Hello everybody, and welcome back to the channel. Today I find myself recording a lovely video at 10 p.m. on a Friday night because I've had quite a bit of work this week. So while all these other 25-year-olds are out doing drugs and partying, I find myself here accompanied by the greatest drug of them all, computer science and meth. That's why I'm able to do this right now. But yeah, today probably not any coding to be done because I did have a busy week, but I was just doing some more general thinking about the problem that I'm trying to solve. So I have another few sets of diagrams that I drew up to try and talk about it a little bit more, and we'll do a little bit of a brainstorming session. I'd love to get some feedback from people in the comments after the fact, so let's get into it. Okay, so I'm going to start this one off by basically doing a little kind of review of what we've got so far, or where we're going so far, and then also introduce a little bit of a new problem in the space and start to brainstorm a bit how to discuss it. When I present these diagrams, I'm actively still thinking about these problems. I don't have a super great solution to them. If I did, that would be great, but I'm still thinking through it, and there are trade-offs associated with anything that I might propose, so I would love to be roasted in the comment section. That actually would really help me out, and it would be very constructive. So please do let me know if you have any ideas, but hopefully we're getting there, which I like. So far we've kind of been iterating on this process of reading data, right? And so what reading data really means is that we want one unified table across multiple different types of data stores, because multiple data stores have different properties that make them better for storing data or querying data. So for example, we've got Kafka, a log-based message broker. This is really nice from the producer side. Ooh, what's that? Motorcycle. We've got Kafka, which is nice to produce rows to because it is a log-based message broker, and so I can write a ton of shit to it really quickly. That being said, a lot of people these days want to be able to see the rows that are in their Kafka or in their Kafka log in their table itself to minimize the amount of data latency between when a row gets published and when it's queryable. So this is still definitely something that we want to be able to support reading from. Same idea, there's also this concept of a transactional database like Postgres or MySQL. In the case of Postgres or MySQL, that's really nice because we can have things like primary keys. You can update a subset of a row, so update only a column or two at once. And just in general, it makes it better because you have indices, which allow you to pick out certain rows of a data set a little bit easier than might be supported in terms of a system like Iceberg. Speaking of Iceberg, we do want to still support that type of thing as well. At the end of the day, the intent here is to build out big data tables that have the capability of serving big analytical queries, but can also take a small chunk of the data set, put them in a database, and then use that for fast modifications, quick searches of individual rows at a particular time, things like that, and then also low latency from Kafka. So we basically want to build this hybrid transactional analytical processing table, which is now a buzzword, but that is ultimately what I'm trying to do here, by virtue of federating queries over a bunch of different sources at the same time. Now, if you recall in our first episode, when you have many different sources of data at the same time and data is actually flowing from one to another to the next, it's important that you be able to view all of them at some sort of consistent and logically consistent snapshot of the data. Because if data is moving from Kafka to our database, and my query engine first reads Kafka and then reads my database, it may actually see the same set of rows twice and not know how to deduplicate those, which is a little bit of a problem. So instead, what we want to end up doing is basically introducing this concept of a data harness. So the data harness, like we've mentioned thus far, is basically telling us what is in our table, right? So the particular data sources, so maybe we've got a Postgres table, maybe we've got a Kafka source, maybe we've got an Iceberg table as well, and we want to be able to read from all of those and union those data sources together. But more importantly, we also need to know what part of those data sources are actually considered valid to be in our table. Because if we don't report that, if we don't provide one transactional, semantically consistent layer over our data, we're going to start having data consistency issues. So let's just quickly draw that out. A really simple example would be something like this. We've got some sort of Kafka topic partition that starts with messages with particular offsets. So we've got offset 0 to 500 in topic X on Kafka. Then we've got some sort of stream job, could be Flink, could be our own thing, that is reading in these messages and writing them out to a database. So they're writing them out to table Y. So after some amount of time, we write the first 250 messages to table Y, and that write completes at time t. So ideally, we want to be using a database here that is capable of actually expressing every single write to it with a particular timestamp. The reason being that we can then go back and read that database back at that timestamp that we were given. So in this case, what we want to do, for example, is let's say this is CockroachDB or something where we actually have that functionality. You write to CockroachDB, you realize, okay, I just wrote to this thing at time t. Now what I can do is go to my data harness and basically say, okay, the valid sources of our table are this Kafka topic X, which we know is only really containing messages 251 to 500 because we handled 0 to 250 already, and that's now in the database, so you don't want duplicate messages. And number two is that we can also perform a read of our database right here as of time t, and that is going to ensure that we are getting both of those data sources there. Now the reason we want to sync into a database, at least to start, is because that minimizes the latency, right? Since databases like Postgres or MySQL or whatever are row-oriented, I can take that row-oriented data from Kafka and put it right into my database. Additionally, if I have multiple rows in Kafka that are supposed to be overwriting each other in the database, that's going to be very efficient if I use an index in my database. Or maybe a row comes in from Kafka that tells me, oh, I just have to update one particular column in this database. That's going to be really, really nice for us as well. It has a lot of good properties when it comes to updating, deleting rows quickly, things like that, because we're staying row-oriented here, and the data is effectively mutable, which is really nice. Now keep in mind that, if you're going to eventually be building up a lot of data, you don't want to keep it all in the database forever, especially if you're running analytical queries where you have to scan in a ton of that data over time. At that point, you want to start syncing out files over to your object store. So you can go ahead and do that, and typically this is when a system like Iceberg would come in, where it's basically just managing a bunch of Parquet files on something like S3 or Hadoop or Google File Storage or whatever. So you've got now a batch job that's moving messages from your database over to your Iceberg table. And at the same time, what that really means is that is going to be updating the valid timestamp of your database, because now we've got a bunch of removed rows, and those rows are getting removed, let's say, at time t plus 3. So we added the rows at time t, maybe they're getting removed at t plus 3. And then the batch job simultaneously now needs to commit those to the Iceberg table, so maybe it does that at t plus 2. Or realistically, maybe t plus 4 or something. It doesn't matter. The point is the batch job is interacting with both of these systems independently, so those commits are happening at different times. However, those commits only actually become visible to our query engine for reading it, like Spark or Trino, when we go to the data harness and update it, right? So we're going to and saying, okay, well now our database is only actually viable as of time t plus 3, so that way when we read the database, we're going to see that a bunch of rows were deleted from it. Similarly, we're also atomically saying, now you have to go ahead and read our Iceberg table as of time t plus 2, and the Iceberg table contains all of the rows that you just took out of this database. So now again, it's not going to ever seem like we have any duplicate data by virtue of having a query engine independently read both of these sources, which is really nice. So finally, what that ends up with is after all these steps, we have a data harness that's basically storing the following table state. We've got, Kafka topic X, which is, presenting messages to us from offsets 251 to 500. Sorry, a little bit of a typo right there. We've got a database table Y, which is reading from time t plus 3. We know from the prior episodes of this series thus far that there are certain databases that support this read pattern. For example, I built that out in Trino with CockroachDB. We can now support reading a CockroachDB table at time t plus 3. Additionally, Iceberg, by virtue of how it's been built, also supports snapshot reads. Definitely work in both Spark and Trino, and you can read an Iceberg table as of a particular snapshot. So right after I commit all of these rows to the Iceberg table, regardless of what happens to it after that, I can still go back and read that table at time t plus 2, thus giving me a consistent view of this table as of that particular timestamp. Another example where this is particularly useful is with schema updates, right? It could be the case, for example, that if we weren't using a data harness, the message schema might get updated in Kafka, and then all of a sudden, you're trying to union those data sources together and you error out because these three sources no longer have the same fields. The reality of it is that what you actually want to be doing is, you can update your message schema in Kafka, and maybe a little bit later you update your database schema, and maybe a little bit after that you update your Iceberg schema. But the only time that actually gets registered is when we tell the data harness, hey, these unified tables have a new schema. Until then, we have to query all of these data sources and kind of coerce their data into the old schema so that we can present that back to our query engine. Cool. So the biggest problem that I continue to face as I think about this in a little bit more depth, because I do eventually want to get to the point where I start writing the data harness itself, as opposed to just writing database connectors for Trino or Spark or Star Rocks or whatever. The biggest thing that I'm thinking about here is concurrent writes. So I'm going to draw out kind of a scenario that's been going through my head and what you'd ultimately want to do about it. So let's go through the situation from before, which is you've got Kafka, you've got a database, you've got Iceberg, and you've got one streaming job going from Kafka to the database, and you've got a batch job that's pulling rows from the database to Iceberg. So basically, let's imagine now that the streaming job and the batch job are both running concurrently, which is kind of the expected workflow here, right? Like you want these to be two different processes probably, and doing their own thing at the same time. So what could happen is if these guys are both running concurrently, and the stream job is adding rows from Kafka to the database, and the batch job is removing rows from the database and adding to Iceberg. God, another ambulance. This is brutal. What can happen is that you have your data harness over here, and basically I can first say, hey, data harness, go and God, this ambulance is coming around. I'm not going to cut this, by the way. I'm just thinking about what I was going to say because I kind of lost my train of thought. Okay, let's imagine basically that 1A and 1B happen at the same time. And 1B operates this database at time t minus 1. So keep in mind that the database gets updated from the stream job at time t, but the database is getting rows removed at time t minus 1. However, the data harness is first hearing that we should be bumping the database timestamp to time t, right? Because we just removed a bunch of rows from the database and then we added new ones from Kafka. So this guy is saying, all right, we're now going to update stuff at time t. And then eventually the batch job is going to go over to the data harness and say, oh, wait, actually, you can now read the Iceberg table at a higher timestamp. And, oh, there are also some removed rows from the database that you have to know about. This is problematic because, before step 3, between step 2 and step 3, this query engine can go read from all of these sources, and it's going to see no rows in the database, or it's going to see that there were a bunch of removed rows in the database that were actually sent to Iceberg. But when it actually reads Iceberg, since the Iceberg timestamp hasn't yet been bumped to t+2, we're not going to be able to see those rows there, and now we're going to have a case of missing data, which is going to be problematic. So the question is, well, what can we really do about this? Sorry, let me get that all out of the way. And it's just like kind of a generalizable concurrent write problem. This is one thing that I personally suffer with in my work when using Iceberg, is that Iceberg pretty much doesn't really support concurrent writes. And the reason is it's hard because, for a database, for example, so much work has been put into, doing this really, really granular, fine-grained locking on every single row to make life a lot easier so that you can update a bunch of rows that are not related to someone else's update at the same time. But when it comes to something like a data harness, we really only have a high-level idea of what sources are involved and maybe just like a timestamp. I'm not keeping track of every single row in a database that's valid or every single row that's invalid, because the amount of data that I would have to store then would just be completely linear to the amount of data that's stored in our system, and that becomes pretty infeasible because these are gigantic systems and I don't want to put that all in a single database. So instead, what you see happening is that we need to figure out a solution here. So to summarize the problem quickly, there are data modifications to some of our underlying systems, and those modifications may make it to our data harness in a different order than the ones in which they're actually performed. And so if that's going to be the case, then we're going to start having problems when reading our data, and we're going to get inconsistent reads. So the main solution that I can think of, at least so far, is locking pretty pessimistically, which is unfortunate, but I can't really think of any other thing to do, which is that, if I've got a stream job and a batch job, and they're both trying to write to the same database instance at the same time, and that database instance only has one timestamp that we keep track of in the data harness, well, basically, they can't do that until the entire data harness is updated, right? So if this stream job is, going to write to this database, before it even does that, it should first grab a lock in the data harness saying, I'm updating the database, no one else can. The batch job may try and do the same, except it's going to realize that it can't grab the lock, so it's going to wait. And then the stream job is going to go update the database. It's going to go update the data harness saying, hey, I'm no longer updating the database. And then the batch job can come along and do the same. Now, this isn't necessarily something that is a desired use case here because, well, it limits our concurrency to be doing this, especially if we've just got one iceberg table, because iceberg tables are partitioned. We've got one database with one timestamp because databases can scale out horizontally and be partitioned. It means that basically only one thing can be writing to each of those at a time. And now all of a sudden our write throughput is inherently very, very limited by the fact that we're using this data harness as a distributed lock. So I guess the question is, how can we partition things out further? Well, I guess the way that we would partition things further, at least as far as I can think of, is that, we would basically just have to take this entire aspect of the problem right here and duplicate it. So what does it really mean? It means you might need multiple Kafka partitions. Now you need multiple databases in your table and maybe even multiple different iceberg tables, thus allowing us to have logical partitions in our table, and thereby meaning that even though there's only one process at a time that can be writing to this particular database or this particular iceberg partition, you'd have a different process that can simultaneously be writing to a different database partition and a different iceberg partition. Now the problem with this is, I'm saying iceberg partition, except the reality is across a single iceberg table, even if you have multiple partitions, there's only one timestamp. There's not a different commit timeline for every single partition in a timestamp in an iceberg table. So for this to actually work, even though technically Kafka partitions are kind of like their own topic, so that's fine, I would have to use different instances of databases and different instances of iceberg tables. And that's when this thing kind of starts to really balloon in complexity, because now all of a sudden I'm basically building my own partitioning mechanism on top of things that already can be partitioned. And that's not great, because it also means that, if this query engine comes along and it says, maybe I implicitly have a bunch of different iceberg tables, and this guy supports, this guy down here supports a subset of the rows, this guy down here supports a different subset of the rows, this one down here supports a different subset. The query engine doesn't actually realize which one of these is responsible for which rows, meaning that it can't really do effective predicate pushdown, unless, of course, I write a shit ton of code to make that happen. Now, that can happen. It actually wouldn't be the worst thing in the world. It'd be cool, but it's also something that's not trivial at all. And you would basically have to make it so that the data that comes in through Kafka is inherently partitioned across the incoming topic in the same way that you want your output iceberg tables or your output database tables to be partitioned. So this could balloon in complexity a little bit. I'm still thinking about what I want to do here and whether that's actually worth it. But yeah, like I said, I'm still very much in the ideation phase of this whole thing here. Number two is that basically we've also got this concept of, this is me musing again. I'm trying to think, rather than doing this whole thing where we've got a bunch of distributed catalogs, because internally Iceberg is actually also using a database to determine what the metadata is for each table. The common way of doing that would be to basically co-locate the metadata storage for your data lakehouse with your actual database right here. So this guy and this guy could technically live on the same database node, and then our data harness also lives on that same database node. So now if you ever want to make commits between your database and your iceberg table and you need to grab a distributed lock in our data harness to do so, what we could actually do is make it so that you don't actually need to grab a distributed lock, you're just grabbing a lock on the actual data harness database, except that's co-located with your catalog for your iceberg table and also your literal data store, right? So remember, we're using CockroachDB. Okay, this is where it becomes a real mindfuck. Please bear with me. I'm sorry. I know I've explained this pretty poorly. So basically, Iceberg, long story, you can't really do what I'm describing. But where you can do this is Duck Lake. So Duck Lake, the idea is it's very similar to Iceberg, but instead of storing all of the metadata for tables on Object Store, all of the metadata is stored in pretty much any Postgres compliant database. So what that means is I could basically run the Duck Lake table on a Postgres database, and then I could also have my data harness on that same Postgres database. However, I can even take that a step further. because we've already mentioned that we want to be using CockroachDB as our like database data store for these tables because it can perform time travel reads. So instead, our data harness, our CockroachDB instance for like storing row data, and our Duck Lake catalog can be on the same physical CockroachDB cluster, meaning that rather than grabbing a distributed lock to make all of these transactions, it's no longer really a distributed lock. We're operating within the same like database cluster the entire time. And so I'm now not building any sort of external systems. I'm just using transactions that are local to CockroachDB. Again, I'm sorry if that's a bit of a mindfuck. I know it's not overly clear. I guess my point is that you're still having one job runner that's taking rows from Kafka, putting them in CockroachDB, putting files on Amazon S3. But when it comes time to actually commit those files or commit those changes to our data harness, a lot of that work is basically going to live on the same database cluster, which makes a lot of it quite a bit faster than using a generic distributed lock. Again, sorry for rambling. It's a little bit late. I don't want to sound too much like Alex Karp, that weird coked up Palantir CEO who swings swords. I swear I'm not like that. No coke, a lot of swords. But point is, the ideations are coming along, and they're coming along swimmingly. So if you did follow along, would love to hear any thoughts that you have. If you didn't, please let me know why you didn't, and I can explain myself better in the comments. But yeah, it's been really cool getting to think about these problems. It's a fun brain exercise for me, and it's a good teaser, so I'm having a lot of fun with it, and I hope you guys are too. Enjoy your Thanksgiving, everyone, and have a great week.